Whether the viewer is interested in incredible profit or in dramatically raising the health and wealth of the world, this presentation will discuss, in a step-by-step perspective, how to create an automated kitchen. Many OEMs are predicting that fully autonomous vehicles will be hitting the market in 4 to 6 years. How will this impact other products such as those in the kitchen? Years ago, science fiction writers pictured vehicles being driven by androids, but this is not how vehicles are becoming autonomous. Instead, sensors, actuators, communications, and emerging complex computation systems are being added to make vehicles autonomous. Robotic researchers are working on expensive androids for the home. However, the same strategy of adding sensors, actuators, communications, and emerging complex computation will bring affordable, autonomous appliances to the kitchen much quicker. The question is, which manufacturers will be first? Imagine a smart refrigerator that is connected to a smartphone and a smart infrared oven or stove. You will be able to instruct your smart kitchen to reheat a frozen dinner that will be ready when you arrive home. Add smart food preparation appliances, and sinks and freshly prepared food will be created in the same way. All of this is well within reach within 2 to 3 years, as the complexity is less than that of autonomous vehicles. How will this impact the kitchen? The layout and construction of appliances, cabinets, and counters will be affected, as will the plumbing, dishes, pots, and pans. Is your business ready, or are you focused only on products similar to buggy whips, which disappeared when horses were replaced by cars? Some contend that automation must be inserted within the existing world. However, from a lowest cost perspective, it is the world that will change as automation is inserted. Kitchens are expensive. For example, they have expensive appliances such as refrigerators, stoves, ovens, dishwashers, toasters, food processors, blenders, sinks, cabinets, counters, and garbage disposals. They have a large space footprint. They have a large number of ancillary devices such as dishes, utensils, pots, and pans. Tossing an expensive Android in only increases the cost of a kitchen. Androids are computationally extremely complex, so complex that they are beyond the possible of the current state of the art. The elements of an automated kitchen, as will be seen later, are reaching the cost of ordinary laptops and appliances. Automated kitchens reduce the number of different appliances, space, footprint, and number of ancillary items. We now dive into the excitement of how an automated kitchen could be created in a step-by-step manner with existing technology. In this model, we will look at a decomposition into 5 fully automated units, 1 purely software unit and 1 partially manually managed unit. The central kitchen unit is the glue that logically connects the other units and runs the show. It does not need any manipulators and may rely upon the computational and communication resources of other units. The food preparation unit is both smarter and more dexterous than current food processors. The cooking unit is a combination of oven, stove, and microwave and is also smart and dexterous. The refrigeration unit includes all cooling and freezing capabilities. The cabinet unit stores all shelf-oriented foodstuffs, dishes, utensils, pots, and pans. Conveyors physically connect all units. The waste unit has minimal automation to open and close different bins and has sensors to signal when it needs manual attendance. Here we have a view of how the pieces physically fit together. Units can have a larger vertical reach than currently exists in kitchens today, as human geometry does not limit layout. Floor space used is thus drastically reduced. Symbols are used throughout the diagrams for conveyors, communications, and sensors, which appear in many locations. While there are 4 primary automated units, we will mostly focus on the food preparation unit, as it is the most complex and the primary enabler of the automated kitchen. Note that there are low automation instances of all of these units in existence today: refrigerators, food processors, ovens, and even smart cabinets. We now dive into the different parts of the food preparation unit. Prepared dishes are created and delivered at this unit. All types of dishes can be prepared: drinks, frozen, cooked, heated, cold, or combination thereof. Dirty dishes and leftovers can also be left at this station for processing. A washing and drying system is included as part of a set of movable implements. Food, packages, dishes, containers, and implements are moved in and out via a conveyor system. Moving blades and other implements for cutting, mixing, placing, peeling, washing, drying food, dishes, and packaging are part of the unit or can be temporarily attached. Implements can move in multiple directions. A rapid rotating platform with moving prongs for gripping and manipulating is included as a base. We now look at how the automated kitchen operates via a dozen examples. Items used in each example are highlighted in red. Usage Example 1. Groceries are delivered to the automated food preparation unit, are separated if necessary, and sent to the refrigerator, freezer, pantry, or cupboard areas. Usage Example 2. New dishes, pots, pans, and utensils are cleaned, dried, and delivered to the pantry cupboard area. Usage Example 3. Cold food, such as fresh fruits and even fresh ice cream, is prepared and sent back to the freezer refrigerator for temporary storage. More temperature gradations will be available than today in both cooling and warming areas for different food needs. Food is moved back to the automated food preparation area for final delivery just before consumption. Usage Example 4. Food is moved from both the pantry cupboard and freezer refrigerator to the automated food preparation unit, unpacked, prepared for cooking, and then sent to the cooking unit where it is cooked. Refuse from unpacking, slicing, and dicing is put into appropriate refuse, recycle, and sewage areas just below the automated food preparation unit. After cooking, food is sent to the warming area just below cooking. Food is moved back to the automated food preparation unit for delivery just before consumption. Final food presentation can be tuned at this time. Here we see a list of possible high-level steps for Example 4. Usage Example 5. The automated food preparation area is used both for a final food delivery as well as a retrieval area for dirty dishes and unfinished portions. Both water pressure and heated air are used in this area to clean dishes, which are then automatically returned to the cupboard pantry area for storage. Usage Example 6. Packaging is automatically removed and sorted into trash and recyclables. Separate recycling bins are available for paper, metal, and plastic containers. Preparation of produce produces biorefuse, which can be stored for reuse as fertilizer. Water pressure takes other biorefuse into the sewage system. Usage Example 7. Dishes, pots, pans, utensils, and storage containers are delivered from and returned to the cupboard pantry area for usage in the automated food preparation area. Usage Example 8. Mobile phones, web, and computer-based applications, microphones, and phones can be used both in written and auditory form to communicate desired food, quantity, and timing. Interfaces include menu options based upon food stores, dietary constraints, dietary preferences, nutrition needs, variety, weather conditions, holidays, and other information. Usage example 9. The system monitors food store levels, food spoilage and expiration, dish breakage, and other issues, providing notifications such as grocery lists when appropriate. Usage example 10. The automated food preparation area can store leftovers in containers retrieved from the cupboard pantry and then send the load over to the freezer refrigerator. Usage example 11. Owners of automated food preparation systems can provide low-level catering services. There are many web-based services that now offer rental of personal vehicles and homes on a short-term basis. Similar web-based services can be created for personal catering and pooling of catering. As software is used to maintain cleanliness and quality of food in these systems, safety and quality can be assured and authenticated. Usage example 12. The kitchen preparation area will require less floor space for counters and cabinets, as storage will be optimized around automated retrieval as opposed to immediate and regular human access. Social and eating areas will be expanded. More in-home entertainment will occur due to the massive reduction of effort required for preparation. Larger in-home social gatherings will occur through web-based sharing of resources such as co-op catering. When looking at the possibility of any project, you need to understand the complexity of its models. The models for an automated kitchen are geometrical space, manipulation, and food. Geometrical space models are common for all emerging automated systems, for example, automated vehicles. Automated kitchens only have a fraction of this type of complexity. They only deal with layers of surfaces in a very controlled and lighted space. Manipulator models are common for all emerging robotic systems, e.g., robotic hands. Automated kitchens only have a fraction of this type of complexity. They only deal with a limited and fixed set of motions with a simple set of actuators. The food model is the most unique element. The level of complexity is in line with common expert systems available at least since the last decade. With respect to food model complexity, state-of-the-art question-answering systems can handle large amounts of information and rules from distributed systems, as would be needed for creating menu options based upon food stores, dietary constraints, dietary preferences, nutrition needs, variety, weather conditions, and holidays. The great diversity of diet and nutritional models on the market requires a nutrition scripting language so that nutritional models can be input. This type of scripting system has been common for over a decade. As a first increment for an automated kitchen, we look at an automated peeler. The elements of an automated peeler include upper holder prongs with a base that rotates rapidly and includes a pressure sensor. A peeler that includes both a pressure sensor and pressure control. And lower holder prongs, which are double jointed, have 3D motion and a base that rotates rapidly. Here we see an existing non-intelligent peeler. An automated peeler would manipulate the fruit and have finer manipulator control so that initial placement is automated and the full fruit is peeled. You can click to see this peeler in action. The complexity of an automated peeler is based on its motion control and vision steps, which are fixed and well understood within existing technology. The other elements of an automated kitchen are all on par with the complexity of an automated peeler. Here we see a manipulator that can handle a broad base of different applications. An automated kitchen would require a smaller set of actions than this more universal type of device. You can click to see this manipulator in action. Intelligent manipulation devices have become low cost. The unit shown is available for a few $100s and includes full computing capabilities. It is composed of a $250 kit upgraded with a $45 microcomputer that runs Linux and possibly upgraded servos. You can click to see this manipulator in action. Full food preparation unit computational complexity is equivalent to the sum of a number of problems of complexity equivalent to the peeler. This includes cutting, upper prong push stir control, placement and removal of unit implements, placement and movement of containers and food processor implement control such as chopping, mixing, slicing, shredding, cleaning, pouring, sequence control, food variety, and pre-processed food package management. Much of the mechanics of universal food processors has already been worked out by multiple different vendors. Only the automated placement and removal of food processor subelements needs to be worked out. You can click to see this in action. Full automated kitchen computational complexity is equivalent to the sum of a number of problems of complexity equivalent to the peeler. This includes temperature control, flipping, food quality management, conveyor control, refrigeration, cabinet, and conveyor cleaning, diet and recipe management, user communication, intra-system communication, inter-system communication, stores control, and authentication. The benefits of automated kitchens include those of food cost reduction. This is because all food can be produced and processed via home automated kitchens and home automated gardens. Further, web-based co-ops can facilitate trading both catering and specialized garden items. Health benefits include balanced diets, elimination of chemical additives and GMOs via usage of fresh produce grown by automated gardens, timely arrival of get-well foods including homeopathic and nutritional remedies, and replacement of unhealthy foods with tasty and fulfilling alternatives. Automated kitchens are but the first step in fully automating homes. Further automation can include items besides foodstuffs can be produced: filtered water, herbal remedies, condensed nutrients, cleaners. Extending into the shop: sewing, shop machines, assembly, and in-home manufacturing. Automated hydroponic gardens. Going mobile: indoor and outdoor gardens, pet feeding, doors, window, blind, and curtain control and cleaning, cleaning bathrooms, carpets, floors, and stairs, picking up, straightening, and dusting, and even mobile 3D printing. This would be for fixing fixed objects. As a final note, intelligent robotic motion can be complex and extremely rapid, as can be seen via this intelligent toy. Click to see it in action.